In this problem, we're given the following circuit diagram. We need to use the Norton equivalent with respect to the terminals A and B and solve for our I and our R. I being current and R being resistance. So when we look at this, we can see that we have a voltage right here. And this voltage is going to impact everything to the right of it. And the right is where we want to look because that is where our A and B is. This is where our current is running through. This is our I of N. And then the resistance is between these two A and B's. This is the resistance we want to find. So everything that we're going to look at is to the right. This means since our actual voltage is right here, we're going to ignore everything to the left. We're just not going to worry about any of that stuff. The first thing I'm going to solve for is resistance. So when I look at this, I need to combine these two resistors, this 15 kilo ohm and this 30 kilo ohm resistor together. However, I can't do that right now. What I could do, if these were both currents, I could add them together, and then 15 kilo ohms and 30 kilo ohms would be in parallel, and I can use the parallel resistor formula to combine those. And actually, I can do that. So using 4.9 source transformations that's linked below in the notes, we can see that we can convert this voltage and resistor that is in series into a current and resistor in parallel. We know that current is equal to voltage over resistance. Our voltage is 30 and our resistance is 15 kilo ohms. So we're going to have 30 over 15. And if we convert this, we're going to get that I is equal to 2 milliamps. This is the conversion from kilo ohms to amps. Kilo ohms to milliamps. So we get that our current I is equal to 2 milliamps. When we look back at our diagram, we know that our voltage is going this way, into the positive, out of the negative, so our current must be going this way. When we redraw our diagram, we're going to have a circle with our current direction inside of it, and then 2 milliamps outside of it, because this is the direction of our current. Then we need to, because of source transformation, have this 15 kilo ohm resistor in a parallel formation. After this, we are going to have a current right here. This is our 10 milliamp current. We're just writing this over. We haven't done anything to it yet. And same thing with the 30 kilo ohm resistor. We haven't moved it, it's just right here. And then lastly, we have our terminals A and terminals B. If we want to find the total resistance for our A and B, all we have to do is take the 15 and 30 kilo ohm resistor and combine them. Since they are in parallel, we have to use the parallel form. This is 1 over the first resistor plus 1 over the next resistor raised to the negative first power. And if we do this, we're going to get 10 ohms of resistance. So the answer for our resistance is 10, and this is in kilo ohms because we never converted it. And we can see from here and here that our units are in kilo ohms. Next, we are going to look at the current. And to do this, we're going to use the Kishkoff's current law. And we have to pick a node. We see that we have a bunch of nodes in our original diagram. I'll put one right here, and we're going to use this one. So we see that we have this 2 milliamp current going into our node. If a current's going into a node, by Kishkoff's current law, it's a negative. So we're going to have a negative 2 milliamps. And I'm just going to omit units here just for simplicity, but this is a negative 2 milliamps. We have a 10 milliamps, and this is going out of our circuit. And lastly, we have current going this way, which we don't know, but this is our I of N. We said earlier that our I of N is this because our current is going out of our node, down this way, and across our A and B terminals. Just like this, it's similar to what we had up here. Since it's going out, it's going to be a plus I of N, and we know all currents going into a node must equal 0, so this is equal to 0. We're going to add all these up, move the constants to the other side, and we're going to get that I of N is equal to negative 8. And this is in milliamps. This is also the answer for our current. That is how you solve this problem. If you have any questions, you can leave them in the comments below. If you want more problems on Introduction to Circuit Analysis, there will be a playlist in the description that'll help you out.